So if you remember back to chapter 3, when we looked at how the different parts of the atom were discovered, we discovered the electron first in the cathode ray tubes. And then we had J.J. Thomson and the Millikan experiment described the structure of an atom as a plum pudding model where you had like random negative and positive charges kind of evenly distributed around the atom. And then you had the gold foil experiment from Rutherford, and he discovered the nucleus and the fact that you had a very dense, positively charged nucleus in the center of an atom making up most of the mass. So we ended up with the Rutherford model of the atom, which is basically the nucleus being a super dense area in the center, and then the electrons kind of going around it, kind of like planets around the sun. However, his model was still incomplete. It did not explain how the atom's negatively charged electrons are distributed in the space surrounding its positively charged nucleus. So basically, how are the electrons spread out around the nucleus? After all, it was well known that oppositely charged particles attract each other. So what prevented the negative electrons from basically being drawn into the positive nucleus? So Rutherford didn't have a way of explaining that. By the way, if any of you have any questions about what I'm talking about, please unmute your mic and ask me. I've hidden your screens because I'm actually recording the Zoom, because then I'll upload it to YouTube if you need to review later. So if you have any questions at all, please stop me at any time and ask me. Okay, so in the early 20th century, a new atomic model evolved as a result of investigations into the absorption and emission of light by matter. The studies revealed a relationship between light and an atom's electrons. This new understanding led directly to a revolutionary view of the nature of energy, matter, and atomic structure. So we basically went from having a basic understanding of the structure of an atom based on the cathode ray tube experiment and the Rutherford Gold experiment. And then when we started looking at how light interacts with matter, it started giving us a more detailed and sophisticated view of the structure of an atom, particularly with, in relationship to the electron specifically. So we have to look at the properties of light and how we understood light up to this point. So before 1900s, scientists thought that light was a wave. This changed when it was discovered that light also has particle-like characteristics. So if we review the properties of a wave, it can help us understand the theory of light that scientists had at the beginning of the 20th century, which was the 1900s. So the first thing we're going to do is look at the properties of light. Now, visible light is part of what we call the electromagnetic spectrum, or EM spectrum, because it's a kind of electromagnetic radiation. This is a form of energy that acts like a wave as it travels through space. There's a lot of different types of energy on the EM spectrum. So just to go through, we've got radio waves down here, and we go up to microwaves, infrared. Here's the visible light. Sorry, is visible light, and then ultraviolet, X-rays, and finally gamma rays. Now you see we've got wavelength here and frequency. These are two of the characteristics of the properties of light as it relates to behaving as a wave. So, like I said, wavelength and frequency, the two properties of EM radiation that we're going to look at. So wavelength, and this is, I believe it's lambda. I think it's lambda. It's a Greek letter that's used to represent wavelength, is the distance between corresponding points on neighboring waves. So for example, let's just draw a wave like that. So the wavelength is either between the crests of the wave from crest to crest, or you can go from valley to valley, but that's the wavelength. So the shorter distance there is between waves, then the shorter the wavelength is. The other property of light is frequency. Frequency is the number of waves that pass a given point in a specific time. Usually that specific time is 1 second. So in these two examples, we can look at both the characteristics of wavelength and frequency of each wave. So for this wave at the top, do you think the wavelength is long or short? Anybody? Hello?
Is it long?
Long or short?
Long?
Long, yeah. Yeah, because you've got a large distance between this wave and that wave. So the wavelength here would be long. What about frequency? Is that going to be high or low?
Low.
Low, yeah. So the relationship between wavelength and frequency is if wavelength is long, frequency will be low because you'll have fewer waves passing that point. Unlike this wave, which has a shorter wavelength, therefore it has a higher frequency because more waves will hit the pillar per second than will this wave. So the relationship between wavelength and frequency is longer wavelength, lower frequency, shorter wavelength, higher frequency. We can actually relate them in a mathematical formula. So the formula is C equals lambda, I think if I'm just going to go with this lambda times V, which is wavelength times frequency, and C is the speed of light. So of course, we know that the lambda or whatever it's called is the wavelength and V is frequency. So because C is a constant, that means the product of wavelength times frequency is also a constant. Do you know what I mean by constant? You know what constant means? In relation to a variable, I mean. It means not changing. So it never changes. C is the speed of light. The speed of light is always 3.0 times 10 to the 8 meters per second. So that's a constant. It's always like that. So if you have C equals wavelength times frequency, if this is constant, it means this together has to be constant. Okay so far? I will take silence as agreement. Yes, everyone's okay. Okay. Here's where the problem starts. In the early 1900s, remember we're starting at 1900, so in the early years of the 20th century, scientists conducted 2 experiments involving the relations of light and matter that could not be explained using the wave theory of light. So up until this point, scientists all agree that light is a wave, but this experiment is going to give them weird results, just kind of like how I explained in the tutorial videos before about Rutherford's experiment and what they expected to see versus what they actually saw. And that's one of the beauties of science, is that you don't go looking for well, I guess you do go looking for an explanation, but you don't start with a conclusion and find evidence to back up what you already believe. You start with a hypothesis or an idea, and you carry out an experiment. If the results don't support your hypothesis, you reject your hypothesis and try to come up with a new explanation. I find in society a lot today, a lot of people, if they have their own conclusion first, they go looking for the facts and the evidence and the articles that support what they already believe, instead of reading things that might make them rethink what they actually believe. So if you find especially when it comes to coronavirus and vaccines. Like, don't even get me started. But too many people don't follow the scientific method, which is like, if you come across information that doesn't agree with what you already believe, then it's your job as a critical thinker and an independent person to say, okay, now that I'm presented with different information, I have to rethink what I believe. And that's the way it should be. Unfortunately, that's not the way society seems to be going at the moment. But anyway, okay, so this experiment is called the photoelectric effect. So what is that? It is the emission of electrons from a metal when you shine a light on it. So you can see based on the little diagram we have here, which is also in your book, that you have, I wouldn't worry about anode and cathode. You'll learn about that later. But the main idea is that you have a metal plate here, and when you shine light on it, then electrons are emitted or released.
Theory of relativity and the Nobel.
Let me rewind. Because if I have my headphone in, then you can't hear it. So here we go.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also... What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect. Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions. So, he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
Okay. So the mystery was that for a given metal, no electrons were emitted if the light's frequency was below a certain minimum, regardless of how long the light was shown. So the basic idea is that, if I go back to here. So the idea behind the photoelectric effect and why the results were so weird is that if light is indeed a wave, then any wavelength of light that you shine on the metal should make electrons be ejected from the metal. But that's not what happened. It was only light that had certain frequencies that would actually cause electrons to be ejected. So what Einstein basically ended up doing was disproving that light was a wave, but also not proving that it wasn't a wave. So he came up with an idea, And that is that it is both a wave and a particle. And I'll explain what I mean by that after I talk about Planck. So this German physicist, Max Planck, was studying the emission of light by hot objects. Because, you know, like if something is really red hot and it's glowing, it's like it still emits light energy as well as heat energy. So Planck proposed that a hot object doesn't emit electromagnetic energy continuously like if it was in a wave. Instead, he said the energy is actually released in small little packets. And these packets of energy he called quanta. So quanta is the plural and quantum is the singular. Plural and singular. And the quantum describes the minimum quantity of energy that can be lost or gained by an atom. So a lot like what Einstein did in his experiment, that light is not a wave and it's also not a particle, but it's actually these little packets of waves that get emitted. And so that's what Planck was describing when he looked at hot objects.
It started not as a crazy idea, but with a light bulb. In the early 1890s, the German Bureau of Standards asked Max Planck how to make light bulbs more efficient so that they would give out the maximum light for the least electrical power. The first task Planck faced was to predict how much light a hot filament gives off. He knew that light consists of electromagnetic waves, with different colors of light carried by different frequency waves. The problem was to ensure that as much light as possible was given off by visible waves rather than ultraviolet or infrared. He tried to work out how much light of each color a hot object emits, but his predictions based on electromagnetic theory kept disagreeing with experiments. Instead, in what he later called an act of despair, he threw the existing theory out the window and worked backwards from experimental measurements. The data pointed him to a new rule of physics. Light waves carry energy only in packets, with high-frequency light consisting of large packets of energy and low-frequency light consisting of small packets of energy. The idea that light comes in packets, or quanta, may sound crazy, and it was at the time, but Einstein soon related it to a much more familiar problem: sharing. If you want to make a kid happy, give them a cookie. But if there are two kids and you only have one cookie, you'll only be able to cheer them up half as much. And if there are 4 or 8 or 1,600,000, you're not going to make them very happy at all if they have to share one cookie between them. In fact, if you have a room with infinitely many kids, but not infinitely many cookies, if you share the cookies evenly, each kid will only get an infinitesimally small crumb, and none of them will be cheered up. And they'll still eat all your cookies. The difference between light waves and kids is that you can't actually have infinitely many kids in a room. But because light waves come in all sizes, you can have arbitrarily small light waves, so you can fit infinitely many into a room. And then the light waves would consume all your cookies. I mean, energy. In fact, all these infinitesimal waves together would have an infinite capacity to absorb energy, and they'd suck all the heat out of anything you put in the room, instantly freezing the tea in your cup, or the sun, or even a supernova. Luckily, the universe doesn't work that way, because, as Planck guessed, the tiny high-frequency waves can only carry away energy in huge packets. They're like fussy kids who'll only accept exactly 37 cookies or 162,000 cookies, no more and no less. Because they're so picky, the high-frequency waves lose out, and most of the energy is carried away in lower-frequency packets that are willing to take an equal share. This common average energy that the packets carry is in fact what we mean by temperature. So a higher temperature just means higher average energy, and thus by Planck's rule, a higher frequency of light emitted. That's why as an object gets hotter, it glows, first infrared, then red, yellow, white, hotter and hotter towards blue, violet, ultraviolet, and so on. Specifically, Planck's quantum theory of fussy light tells us that light bulb filaments should be heated to a temperature of about 3,200 Kelvin to ensure that most of the energy is emitted as visible waves. Much hotter, and we'd start tanning from the ultraviolet light. Actually, quantum physics has been staring us in the face since long before light bulbs and tanning beds. Human beings have been gazing into fires for millennia, with the color of the flames spelling out quantum all along.
Okay, so I think his cookie analogy got a bit confusing, at least I think that for you guys it might do. But basically what I want you to understand is what he was talking about with the cookies, and that you have some kids that only want 36 cookies or 37 cookies or whatever. He was trying to make that analogy between the amount of energy that's in each quantum. So for this one, you've got this light bulb is releasing all of these different packets or quanta of energy, and each packet contains a specific amount of energy based on what you can see here in the diagram, the frequency, which corresponds to a color. Now I want to go back to this. So I want to relate wavelength and frequency to color. So you see here we got the visible light spectrum. Does everybody know the colors of the rainbow? Because that's our visible light. And there's an acronym that you can use to remember. Roy G. Biv. So we've got red, orange, yellow, green, blue, indigo, and violet. And that describes the colors of the rainbow here. You can see them down here in order of increasing frequency and decreasing, decreasing wavelength and increasing frequency. See, this gets confusing. So at the lower end of the frequency, you've got red, and at the high end, you've got violet. And that's why below red, you have infrared, and above violet, you have ultraviolet, right? UV light from the sun, because it's all based on wavelength. So you've got specific ranges of wavelengths that correspond to specific colors of light. And so that's what, get rid of that marker thing. That's what he was talking about in the video based on, where is it? Here. So you can see here when he's using red, orange, green, and blue. Red has the longest wavelength and the lowest frequency, and blue and violet have the shortest wavelength and the highest frequency. So when you look at, Planck was studying hot objects, but when you look at hot objects or objects that emit light, they release the light, again, in these little packets of energy, and each packet of energy contains a very specific amount of energy. And that's what he was talking about when he said, like, some kids only want 37 cookies, not 36, not 38, but 37. I'm hoping that kind of makes sense. So Planck projected the following relationship between a quantum of energy and the frequency of radiation. So he said E equals HV. So let's look at each of those variable. In the equation, E is energy in joules of a quantum of radiation or energy, light, whatever you want to call it. V is a frequency, and H is something called Planck's constant, which you do not have to remember, but that is 6.626 times 10 minus 24 joule seconds. But that's now known as Planck's constant. So basically, what does all this mean? All of this means is that before Einstein, scientists agreed that light was a wave. Then you look at the photoelectric effect, and you observe that there is a minimum amount of energy of light, or frequency of light. I'll say frequency. There's a minimum frequency of light that will make the metal eject electrons, but that does not match the wave theory of light, because if light is a wave, then any frequency of light should cause electrons to be emitted. So when Einstein came along and said, well, maybe it's not waves, and it's not particles, but they are particles that are made of waves. And the easiest way I can explain to think about this is when you think about an actual wave of like in the ocean, you have the wave, but it's made of water particles. And so if you think about light being that wave, but the particles are these quantum packets of energy that are being released from the source of light. Any questions so far? Okay, so after Planck, talking about you've got little packets of waves, and so those waves correspond to frequencies. The higher the frequency of the wave in the packet, the more energy that packet is carrying. And so then Einstein took that idea and then introduced the idea that all EM radiation is both a wave and a particle. So it's not one or the other, it's kind of, it has properties of both. So light can have the properties of waves, but it can also be thought of as a stream of particles, a lot like I told you the analogy of like a wave in the ocean, even though the wave can be looked at as one entity, but if you zoom in at the molecular level, it's actually made of lots of little particles. Einstein called these particles photons, and that is what we call them now, the little packets of energy that are released in any form of EM radiation is called a photon. So now we can adjust our equation so that we have the energy of a photon, which Planck before had as a quantum, is equal to Planck's constant times the frequency. So basically, if this is constant, if H is constant in math equations, you can basically ignore constants because they never change. So the energy of the photon, and this is the main point of this part, I guess, the energy of the photon is directly related to the energy of, or sorry, the frequency of the radiation. Again, the higher the frequency, the higher the energy of the photon or the little quantum of energy that's being emitted. Any questions so far? You're like super, super confused and like, oh my God. Okay, what I'm gonna do